Headlines in 2026 claimed physicists had figured out how to send messages backward in time. That sounds like science fiction, so what did they actually prove? And does quantum physics really let you text yesterday? To answer that, we start from zero. Not with time machines on the first slide, but with something you already live inside every day. Cause and effect. You drop a mug and it shatters. The drop comes first and the shatter comes second. That order feels like a law of reality itself, and for almost everything in daily life it is. Classical physics is the physics of everyday objects, balls and cars and planets. If you know where something is and how fast it is moving right now, then the equations tell you where it will be next. In other words, the past plus the rules equals the future. Information flows one way from earlier to later. When scientists say causality, that is what they mean. Causes before effects. No surprises in the normal world. Quantum mechanics is the separate rulebook for extremely small things. Electrons and photons and the components inside atoms. Here is the part an ordinary person actually needs. At that tiny scale, particles are not little marbles sitting in one place waiting to be seen. Before you measure them, the math describes odds. The particle might be detected here or there, and the equation gives you probabilities, not a single guaranteed answer. Then you measure. You click a detector or record a photon on a screen. The range of possibilities collapses down to one outcome you can write in a lab notebook. So quantum mechanics is brilliant at predicting the statistics of many trials, but it leaves a famous argument open. What was the particle doing in the instant before the measurement? Different interpretations disagree on that, but they agree on a lab rule. You cannot rerun history and cherry-pick the outcome you wanted while still calling it a fair experiment. Unless you cheat in a very specific way that physicists can write down on paper. That cheat is the spine of this whole story. Before we get to time, we need one more everyday idea dressed in physics language. In physics, a message is just information that removes uncertainty. If I flip a coin, hide the result, and later tell you heads, you received one bit of information. You went from 50-50 to sure. A communication channel is any pipeline that carries information from a sender to a receiver. A fiber cable, a radio link, even a carefully prepared pair of quantum particles. Engineers ask a practical question. Through all that noise, how many bits per second can you still deliver reliably? That ceiling is called channel capacity. Think of it as the top bitrate of the pipe. It becomes central when we talk about messages to the past. Now the science fiction vocabulary, but built from the ground up. General relativity is Einstein's theory of gravity. It says space and time are woven together into one fabric called spacetime. Mass and energy bend that fabric, and bending is what we feel as gravity. A closed timelike curve is jargon for a path through spacetime that loops back and meets your own past. In plain language, a time loop. Einstein's equations allow such loops in certain extreme solutions, like the inner region of a spinning black hole or some wormhole geometries on paper. Building one in a lab is a different category of problem. You would need to bend spacetime with energies and densities far beyond anything humans can produce. So theorists do what engineers do when the hardware is impossible. They substitute a mathematical model that captures the hard part they care about. That substitute is called a postselected closed timelike curve, or P-CTC for short. Seth Lloyd at MIT and collaborators published the framework in 2011. It does not bend spacetime in a basement. It uses quantum teleportation plus postselection to mimic a time loop inside the equations. Quantum teleportation sounds like Star Trek, but in the lab it means moving a quantum state from one place to another using entanglement and classical messages. No object gets physically scanned and rebuilt. Entanglement means two particles can be linked so that measuring one instantly correlates with the other no matter how far apart they are. Einstein called it spooky. It is real and well tested. Postselection is the cheat. You run a quantum experiment many times and throw away every run that did not give the outcome you pre-chose to keep. In other words, you discard almost all the data and analyze only the rare branches that fit your condition. That is not free. The rarer the branch, the more attempts you need. The surviving runs can show patterns that look like information flowing backward, even though nobody literally traveled to yesterday. Lloyd's team also ran a small photon experiment in 2011, showing that this post-selected model resolves grandfather paradoxes by giving impossible loops zero probability. So you do not erase yourself by killing your grandfather in the model. Paradoxical histories simply never survive the filter. That brings us to the 2026 paper that drove the headlines. Kaiyuan Jai at Cornell, Mark Wilde at Cornell, and Seth Lloyd at MIT published in Physical Review Letters on June 11, 2026. The title is deliberately dry: Retrocausal Capacity of a Quantum Channel, Communicating Through Noisy Closed Timelike Curves. Retrocausal is the adjective for influence running backward in time inside a model, not a claim that your phone can ping last Tuesday. They borrow the movie Interstellar only as a picture. A father in the future tries to send data to his daughter in the past through an imperfect link. In the film, the gimmick is gravity and a tesseract. In the paper, the link is a noisy quantum channel standing in for a post-selected time loop. A quantum channel here means a noisy process that takes a quantum state in and spits a degraded quantum state out. Photons get lost. States get mixed. Real imperfection. The sender sits in the future. The receiver sits in the past. The team asked one precise question: what is the maximum bitrate for reliable messages sent backward through that setup? They answered with exact formulas for retrocausal capacity. That is the name for the backward bitrate limit in this model, not a product you can buy. The formula uses two technical scores physicists already had on the shelf. Max information measures how much of a message the noise still preserves. Doblin information measures how thoroughly the noise scrambles what went in. Here, those abstract scores finally get a plain job description as bits sent backward under stated rules. Here is the surprise that made editors pay attention. Inside this post-selected loop model, backward messaging can beat forward messaging through the same noisy channel. Read that carefully. Same noise on the wire. But the retrocausal setup also includes a causal loop and a quantum memory the ordinary forward setup does not get for free. Why the boost? The sender can encode using memory from both sides of the loop. The daughter leaves a record the father later reads before he sends backward. That closed-loop strategy is what unlocks extra capacity. It is impossible if information only ever marches past to future in the usual way. So the headline is not "Build a time phone tomorrow." The headline is "We now have a rigorous bitrate limit for backward messaging inside this specific quantum model." The 2026 work is theory on paper. No new basement time machine, no detector printing tomorrow's stock prices. It connects to black hole research, because some final state models describe Hawking radiation using post-selected teleportation ideas in the same family. Horowitz and Maldacena proposed one famous version in 2004. It is controversial and unproven, but it is why theorists care about retrocausal capacity at all. What did the paper not prove? It did not prove you can send a WhatsApp to last Tuesday in the real world. There is no lab device here. No spacetime bent in a warehouse. Post-selection means throwing away almost every experimental run which may scale so badly it never becomes useful communication. And the whole story still assumes quantum mechanics and general relativity can be stitched together, where both apply, which is exactly the unfinished fight called quantum gravity. So where does that leave you on causality? Your coffee still spills forward. Deadlines still approach. Aging still runs one way in daily life, because heat disperses and statistics push the large-scale world toward disorder. That is the thermodynamic arrow of time. But in foundations physics, the strict one-way story gets questioned. Entangled particles show correlations that naive classical stories struggle to explain. Some researchers explore retrocausal models for those correlations. That is a minority view, and it is not settled. The 2026 capacity paper is still valuable even without a time phone. It turns backward messaging from a meme into a number theorists can compute once noise is honest. 3 open questions remain. Can any of this ever be tested without post-selection cheats? Does retrocausal capacity describe black holes or only our math tools? And if backward channels beat forward ones on paper, does that hint time itself might emerge from information? No clean answers yet. Here is what most people assume. Cause always comes before effect. The past is fixed. The future sends nothing back. The 2026 result pokes at that certainty only inside a post-selected model on paper, not with a machine in a garage. You are likely wrong if you think causality is perfectly ironclad at every layer of reality. The math allows backward messaging limits in that model, and sometimes backward beats forward there. The fact on the ground is simpler. Your morning still runs forward, but the deepest rulebook may not be as one-directional as you were taught.